So the numerical says find deflection at point B and C. That is, this is B and this is C of cantilever beam shown in figure. Cross section of beam is 150 by 250 mm. Take E is equal to 200 gigapascal. Now, the method what we are going to use, if you see in the books for cantilevers, he has derived the formula. They have derived some formulas for point load at end, point load at center, or point load at any distance. What will be the slope and deflection for UDL? What will be the slope and deflection? Now here there is a UDL and a point load. So they use both of those equations to find the deflection and slope at various points, and they combine them together and they find the answers. So for that you will have to remember number of complex equations, which is not possible, right? And you will not get full marks also if you just write some equation and put some values in that. So what we'll be doing is we'll be solving this also using Macaulay's method of double integration, and we'll try to solve it. Now in case of simply supported beam, we always took the origin as the left side support, and we took a section X with respect to this section. Now in case of cantilevers, we should always choose a section X close to these support, right? So in this section AB where there is no load, I have to take a section XX, and with respect to the free end, I have to find the bending moment on that section, and based on that derive an equation and integrate. That is the main difference between simply supported beam and this cantilever beam. Rest all things are same. There is no difference as such, right? Another main thing that you have to remember is for cantilever beams, you don't have to find the support reaction. That is not required at all, right? You don't have to find what is RA. If you have to take section XX somewhere here, then you have to find RA and do a lot of things. So by taking section here, I'm eliminating that step of finding the reaction at the support. So without that, directly you can start with the solution. All right. Now, since I have a UDL here, which is not for the full length, so whenever you have for some part of the length, in that case, it is better you extend this till the section XX, and then provide a compensating UDL at the bottom, right? Though this is starting from this point, uh, for us to make things very easy, and for you to understand how to handle the UDLs, we will try to do it here also. So I'll just copy this sketch here, and we'll do the modification to this. What is the modification? First of all, I will take my section here, right? So this is my section XX at a distance of X from the free support C. Now I have to extend this UDL till this point. So let me just do this. I'm just extending the UDL now. The magnitude of UDL would be same, 2 kilonewton per meter. Now to compensate for this additional UDL, what I will do is I will copy this and put it in reverse direction, right? So this is my additional UDL. So here I have added additional UDL in the opposite direction. Now let me just name these things. This is section X, and this is point X, right? Now from here to here this will be X. So from here this is X minus 1, and from here to here this is X. Let us just write that down. This is X minus 1 meter, and this is X, right? So with this changes, we will take this sketch to our solution. Uh, Consider a section XX at a distance of X meter from the free support, the end of okay. So this is the figure. So I'm considering the section XX at a distance of X from the free end of the cantilever. Now bending moment at section XX is given by, so from here it will be same, right? Now what is the bending moment here? It will be mx, and that is equal to if you see all the forces are vertically downwards, this is vertically upwards. So this upward force is making a counterclockwise couple. So right side counterclockwise will be positive, and this is making uh, clockwise couple. So these forces, this couple will be negative, right? So let us start with this. Minus, I have 1 kilonewton, 1 into x, right? 1 into x minus 2. The length of UDL here is x, and it is acting at x by 2 distance from this support, right? So x into x by 2, or it will become x square by 2. It is 2x square by 2. Then I have this compensating UDL which I have added. So this will be positive. So plus the intensity of this is also 2 kilonewton per meter. So it is 2 into x minus 1 is the length into x minus 1 into x minus 1 by 2, because midpoint of this xb is the force that is acting. So I will make this as x minus 1 into x minus 1, so it will become x minus 1 whole square by 2, right? So this is the equation for bending moment at x. Now I'll just simplify this. So this is equal to x, sorry, minus x minus x square plus 2 by 2 gets cancelled. Here also 2 by 2 gets cancelled. So what remains is x minus 1 whole square, right? So this is my uh, equation for finding the bending moment at any point x from the free end. Now we also have mx is equal to ei into d square y upon dx square, right? Now we equate these two. Equating both, we get ei d square y by dx square is equal to minus x minus x square plus x minus 1 whole square, right? So this is my equation which I have to integrate now. Integrating above equation, we get this ei remains as it is. So ei into d square y by dx square upon integration will become dy by dx, and that is equal to minus x will become minus x square by 2, correct? Minus x square is there. I'll just better copy this, that is easy. So x become x square by 2. I have x square, so this will become x cube by 3, and x minus 1 whole square is there, so this will become x minus 1 whole cube by 3, right? Plus add constant of integration c1. So this is my equation 1 from which I will find the slope later. Sorry? Okay. Now I have to integrate this equation again. What do I get? ei dy by dx will become y is equal to x square by 2 will become x cube by 2 into 3, x cube by 3 will become x raised to 4 by 3 into 4. Same with this, x minus 1 raised to 4 by 3 into 4 plus c1 x plus c2. We call this equation 2, right? So now from this I can find slope, from this I can find the deflection, but before that I need to find the constant c1 and c2. Now in order to find the constant, I need to apply the boundary condition, right? So what boundary condition I can apply? Now let me quickly, where is my, this is, yeah, right? So because of load, the beam will bend like this, right? So the beam is going to bend like this, and when we extend this, this will be like an arc of a circle. So when you extend this, you will get a circle like this, right? Something like this. So this is the deflection, and it will be like this. Now the slope at the support and the deflection at the support will be 0 for cantilever. I repeat again, the slope and deflection both are 0 at the support for the cantilever beam. Whereas in case of simply supported, we used to take the deflection only at the support is equal to 0. That was our boundary condition. For cantilever, we will take slope is equal to 0 at support and deflection is equal to 0 at support, right? So by using these two boundary conditions, we can calculate this. Now let us apply the first boundary condition. Applying boundary condition at x equal to L equal to 2 meter, y is equal to 0, right? Or yeah, y is equal to 0, right? In equation 2, right? So we get, let me just copy this equation. Now I have to put y as 0, so this term will become 0. X value is 2, so this will become 2 cubed by 2 into 3 is 6, 2 raised to 4 by 3 into 4 is 12. 2 minus 1 is positive, so I will take this one also. 2 minus 1 raised to 4 by 12 plus c1 into x. So it will become 2 times c1, right? So I am not able to find either of the constants, but I will get a relationship between c1 and c2 here. Um, let me us calculate this. What is this? Let us start from this. This is 2 minus 1 is 1. 1 by 1 by 12. 1 by 12 minus this part 2 raised to 4, right? 2 raised to 4 by 12 minus 2 cube is 8 by 6. So it is minus 2.583, right? So, or minus 2.583. Just copy this. 2 times C1 plus C2 is minus 2.583. So this is a relation I have got. Now what I have to do, I have to put the other boundary condition in equation 1. So from that I will get C1, then I will find C2. Now rather I should have done that first. Let me do it like that. Applying boundary condition at x equal to L equal to 2 meter, dy by dx is equal to 0 in equation 1. We get, now let me just copy this. Dy by dx is 0, so this will become 0. This is x square by 2, so it is 2 square by 2. This will become 2 cube by 2. This is 2 minus 1 positive, 2 minus 1 whole cube by 3 plus C1, right? Or C1 is equal. Now let me calculate C1. This is positive. 1 minus, 2 minus 1 is 1. 1 cube is 1. 1 by 3. 1 by 3 minus 2 cube by 3. 2 cube is 8. 8 by 3 minus, this is 2 raised to 2. That is 4 by 2. So this is minus 4.3. So when it goes on the other side, it will become plus 4.33. Or C1 is 4.333. Right? Now here I will put C1 value as 4.333 in this 4.333, so that I will get C2 now. C2 is equal to, let us calculate. So 2 into 4.333 plus this will be 1 by 12. 1 by 12 minus 2 raised to 4. 2 raised to 4 is 2 cube is 8. 8 into 2 is 16. So 16 by 12 minus 2 cube is 8. 8 by 6. So it is a positive value 6.0826 or 6.083. and when it goes on the other side it will become negative. So C2 is minus 6.08. Now I have both constants C1 and C2, so equation 1 and 2 can be rewritten. Now equation 1 written as EI dy by dx, all these things remains as it is. C1 is 4.333. Just replace that 4.333 and call this equation as 3 now. And equation 2 can be written as, just copy this equation here. Let me just do the simplification. 2 into 3, it becomes 6. This becomes 12. This is also 12. C1 is 4.333. 4.333 x plus C2. C2 is negative, so it is minus 6.083. Now this equation number 4. Now what he has asked in the question, deflection at point B and C, this and this, he has not asked the slope, right? We can find the slope also, not a problem. So first let us find deflection. Deflection at C. Now what is the point C? C is the free end. I have taken x from the free end. So x will be 0. X equal to 0. Right? So I have to put x equal to 0 in equation number 4. Put x equal to 0 in equation 4. We get okay. Before that, I need to calculate EI value. Cross section is given here, so I have to calculate the moment of inertia. So this is 150 by 250, right? Or let us do it in the beginning. Moment of inertia of the beam section I is equal to BD cube by 12. It's a rectangular section, BD cube by 12. So B here is 150, 150 into depth is 250 cube of that by 12. So this value will be 150 into 250 cube by 12. That's a huge. This will be mm raised to 4, right? I want this in meter raised to 4 so that my calculation becomes simple. So mm raised to 4, to convert this into meter raised to 4, I have to divide by 10 raised to 12, right? So by 12, 10 raised to 12 equals, so it is, I better just copy this, which is equal to this, and the unit is meter raised to 4, right? Now EI is equal to, see the bending moment, what we have calculated here, this is in kilonewton meter, because all the force is in kilonewton and lengths are in meter, right? So I have to take this EI also in kilonewton meter square. So E is how much? E is 200 gigapascal. So to make it into kilo, I have to multiply it by 10 raised to 6. So 200 into 10 raised to 6. So this has become kilo pascal. Just put it in bracket so that we don't get confused. Into this in meter raised to 4. So this is equal to, just copy this value. Now 200 into 10 raised to 6 into 6 10 raised to 6 into this. So this product is this much EI, and this unit is kilo newton meter square, right? So this is called as flexural modulus. Now I have to use this as my EI. So let us go here. We get Y is equal to, this EI will come as division on the other side, so it is 1 by this value, and use a bracket, and I'll copy this entire expression, this is minus, right? Now you put x as 0 in all these places. Now when you put x as 0, this will become 0, this will also become 0, 0 minus 1, so this will become negative, so drop this term. This multiplied by 0, this will also be 0. So only thing that remains is minus 6.083, and divide that by this. So 6.083 by 39062.5. This is equal to negative of this 000155. I'll truncate it here, 6 meter, which is equal to, that's very less, it will be 0.156 mm minus 0.156 millimeter is the deflection at the free end, right? Then we need to find deflection at point B. Now how to find deflection at point B? Put x as this length BC, which is 1 meter. Deflection at B, that is x equal to 1 meter. So I'll again just copy this expression, multiply by this, put a bracket and put this inside here. Now substitute x as 1. Now if I put x as 1 here, it will become 1 cubed by 3. This will be 1 raised to 4 by 12. 1 minus 1 will become 0. So this term will be 0. This is into 1, so it will remain as it is. This is a constant, so no change. So now let us calculate all this. Minus 1 by 6 minus 1 by 12 plus 4.333 minus 6.083. It is minus 2 by 39062.5. This much meter, which is equal to 0.0512 mm. 0.0512 millimeter. See, the section is quite heavy. It is 150 by 200. It's quite heavy section. So for this much loading, the deflection is quite less, right? So this is the solution. If you want, you can also find the slope at these 2 points. It is not asked. I still have another 4-5 minutes. Let me just find the slope also. For slope, you have to just use this equation, right? In this, put the value of x, you will get the value of slope into it, right? So in that way, you can find slope and deflection.